Have you ever pondered the implications of traveling at the speed of light? Imagine hurtling through the cosmos, clocking in at a staggering 299,792 kilometers per second. This isn't just any arbitrary figure. It's the universe's ultimate speed limit, known as the speed of light. According to Albert Einstein's renowned theory of relativity, nothing in our universe can travel faster than light. It's a cosmic law of sorts, a limit that all matter and energy must adhere to. This speed limit shapes the fabric of space and time, orchestrating the cosmic dance of galaxies, stars, and even the smallest particles. But it's not just about physical entities. Light speed also governs the way information travels, influencing how we perceive the universe around us. It's an essential part of the cosmic rulebook, a fundamental principle that underpins our understanding of reality. But what if we could break these cosmic speed limits? What would happen then? Imagine, if you will, a daring explorer named Alex embarking on a journey at the speed of light. Picture this: Alex, an intrepid adventurer, has decided to challenge the very laws of physics. With a spacecraft designed for light-speed travel, he plans to traverse the cosmos at a speed no human has ever reached before. But what would such a journey entail? As Alex's spaceship accelerates towards light speed, time begins to warp in strange and fascinating ways. This is a concept known as time dilation, which states that time slows down the faster you move. To Alex, the journey might seem to pass in a mere blink of an eye. However, back on Earth, years or even decades could pass. Time dilation is not just a figment of science fiction, it's a real phenomenon, confirmed by countless experiments and observations. If Alex could look back at Earth while he's traveling at light speed, he would see time on Earth passing incredibly quickly, like watching a movie on fast forward. Alex's spacecraft itself would undergo a bizarre transformation as well. According to the theory of relativity, as an object approaches the speed of light, its length appears to contract along the direction of motion. This is known as length contraction. So, from Alex's perspective, his spacecraft would seem normal. But to an observer back on Earth, the spaceship would appear squished, growing shorter and shorter as it approaches light speed. But here's the catch: our current understanding of physics tells us that no matter can travel at the speed of light. As Alex's spacecraft gets closer and closer to light speed, its energy and mass would increase exponentially. The energy required to push the spaceship to light speed would theoretically be infinite. This means that, as fascinating as Alex's journey might seem, it's currently beyond the realm of possibility. Furthermore, traveling at light speed would also mean that Alex would not be able to see anything in front of him. The light from objects in his path would reach him at the same time he does, resulting in a bizarre visual phenomenon. The universe in front of Alex would appear as a bright, unresolvable blur, while the universe behind him would be plunged into darkness. Our daring explorer Alex serves as a testament to the strange and fascinating realities that arise when we venture into the realm of light speed. His hypothetical journey challenges our understanding of time, space, and the very fabric of the universe. But for now, these challenges remain just that, hypothetical. Despite our progress in technology and understanding of the cosmos, the speed of light remains a cosmic speed limit that we've yet to overcome. So we see, traveling at the speed of light is not as straightforward as it might seem. One of the most mind-bending aspects of light speed travel is the phenomenon known as time dilation. Now, let's step into the world of time dilation, a concept that may seem straight out of a science fiction novel, but a reality according to Einstein's theory of relativity. Imagine our adventurous Alex embarking on a journey, traveling at the speed of light. As Alex accelerates to this cosmic speed limit, something peculiar happens. Time begins to slow down for him. Yes, you heard it right. Time, as we know it, is not absolute. It is relative and can stretch or shrink depending on how fast you're moving. This is the essence of time dilation. So while our brave Alex is zipping around the cosmos at the speed of light, his onboard clock is ticking slower than the clocks back on Earth. Every second for Alex is longer than a second for us. Now, this doesn't mean Alex would suddenly start moving in slow motion, or his heart would beat any slower. From his perspective, everything would seem normal. This is because time dilation is not something you experience, but rather something that becomes apparent when comparing two different frames of reference, one moving at a high speed, like Alex, and the other stationary, like us on Earth. Now let's say Alex returns to Earth after what seemed to him like a year of travel. He might be expecting a warm welcome back party, but instead he would be in for a shock. He could find himself in a world where everyone he knew is aged or perhaps no longer around. Because while only a year has passed for Alex, due to time dilation, decades or even centuries could have passed on Earth. He would be like a time traveler thrown into the future, all because he dared to travel at the speed of light. In essence, our brave explorer Alex could return from his journey to find that decades or even centuries have passed on Earth. Beyond the effects on time, there's another peculiar reality Alex would face on his Lightspeed journey: length contraction. Now, this concept may sound like something out of a science fiction novel, but it's a very real aspect of physics. It's part of the strange and fascinating world of Einstein's theory of relativity. When an object moves at speeds close to light speed, its length appears to contract for an observer at rest. This contraction only happens in the direction of motion. So if Alex were to look out of his spaceship window while traveling at light speed, he would observe the universe as if it had been squashed flat. The stars and galaxies in front of him would appear compressed, as if someone had squished the cosmos with a cosmic rolling pin. Now let's get something straight. Objects don't physically shrink down when they move at light speed. Their actual size remains the same. It's all about perception. The contraction is a result of the way space and time intermingle at such extreme velocities. Imagine Alex is flying past a stationary planet. From his perspective, the planet would appear flattened. It's not that the planet is actually pancake-shaped, but from Alex's vantage point, moving at the speed of light, that's how it would appear. It's important to remember that this length contraction wouldn't just affect the way the universe looks to Alex, it would also change his perception of distance. What might be millions of light years across in our stationary perspective could, from Alex's point of view, be traversed in a much shorter time. In essence, the faster Alex travels, the smaller the universe appears to him. The distance between stars contracts. The length of the Milky Way shrinks, and even the vast gap between galaxies seems less intimidating. Thus, not only would time become a variable entity for Alex, so would space itself. So, what have we learned from Alex's hypothetical lightspeed journey? We've taken a journey through the cosmos, and it's time to tie together the threads of our exploration. Our first stop was the concept of the speed of light as a cosmic speed limit. This is not just a number, it's a fundamental constant of nature, and it's fast, very fast. Imagine traveling around the Earth 7.5 times in just 1 second. That's the speed of light. But as we've seen, this ultimate speed limit isn't just about how quickly light can travel. It's woven into the very fabric of space and time. The speed of light is like a cosmic speed limit, a boundary that nothing can surpass. It's a fundamental part of our universe's rulebook, one that governs everything from the smallest particles to the largest galaxies. Next, we delved into the peculiar effects of light speed travel. The first of these is time dilation. As we approach light speed, time slows down for us relative to an outside observer. This isn't some abstract scientific theory, it's a proven fact that's been tested and confirmed in countless experiments. And then there's length contraction. As we speed up, distances in the direction of motion appear to shrink. It's another strange but real consequence of our universe's speed limit. These effects might seem bizarre, even unthinkable, but they're a part of the reality of our universe, a reality shaped by the speed of light. They show us that the universe isn't just a stage where things happen, it's an active participant with its own rules and behaviors. While we may not be able to journey at the speed of light, understanding these concepts gives us a fascinating glimpse into the nature of our universe. The speed of light isn't just a number, it's a window into the deep, fundamental truths of our cosmos.